Alright, so I have started streaming. We still got about 2 more minutes to go. So, we are. I'm just having fun with Google right now. Yeah, the universal translator is getting pretty close these days. Just a little Bluetooth headset, and Google Translate, set to the correct mode of operation, and we almost have we almost have the universal translator. What Star Trek did not have is the concept of Big Brother. The Federation is always listening in to your conversation, regardless of what language you are using. We are universally eavesdropping. I think that part was kind of neglected in the Star Trek universe. So I thought, I just found it kind of interesting. Yes, I am recording. I'm streaming right now. All right. Good morning. So I'm just gonna stick with good morning because I think almost everybody understand that one. So there we go. All right. So let's go ahead and get started. It is 9 a.m. So if you check the lab from Tuesday, the answer should be disclosed now. I set it up so that you can go back to a lab and you can check your own answers, and also it can also serve as a resource so you can study from the lab as well, because you probably noticed by now the lab actually has quite a bit of instructions, and also it also has its own knowledge and content that relates to the class. All right, so what you're seeing here on the screen, let me make sure that I'm not covering. Yep, oh, we're good. So what you're seeing here is my map for today. So in other words, every morning, before class, for this class, I spend about, I would say about 15 minutes or so to come up with, something like this, okay? Because I want to be able to remind myself and also to remind you, what concepts we are supposed to have understood or we have talked about already. So, at the very early part, we have and or not, NAND, and so also the transistors. And then we talked about base conversion. I completely forgot to put to base conversion here. And then we talked about more recently on Tuesday, we talked about single digit sum, which is the R function, single digit carry, which is the C function. And then we defined the terms, Qi, Ki, and then Si. We talked about notations in Boolean expressions because I'm too lazy to use the proper mathematical and the proper mathematical or operators, and also the proper mathematical negation operators. So instead of using the and operator, it looks like multiplication with no operator in between. And instead of using or, I'm using the plus symbol. And instead of using the negation symbol, I'm using exclamation point, which is obviously chosen because of C and C++ and all the languages that are related to C and C++. And then we talked about, the R function for all bases up here. And then we specifically talked about, the R function for base 2. In other words, base 2, is kind of like Boolean, except, we have multiple places where you can expect a Boolean value. So for the most part, anything that works in base works for Boolean would also work for base 2. So at that point, we found out that the R function can be done using exclusive OR. Let me magnify this a little bit so you can see the operator. So there we go. So the R function can also use the exclusive or if you do not want to use exclusive or, we can use this kind of longer but equivalent expression. We talked about these things, and we also talked about the priority. Negation has the highest priority, so without the use of any parentheses, negation will always be applied to whatever is immediately to its right hand side, and then followed by conjunction. Conjunction will always be performed first before disjunction if there are no parentheses indicating the ordering of the operations. And then carry is the easy one. It's just x and y, and now we are using the shorthand, and therefore it looks like x times y. So these are all the concepts that we have talked about already, and I think people really need to be comfortable with these concepts, before they can integrate the new concepts that we are going to talk about today. So what we'll be talking about today is the carry ripple adder, which relies on the relationship of ki plus 1 depending on k of I. But then we'll also talk about propagational delay. It is a very simple design. It's very scalable, but at the same time it is also quite slow because we have propagation of the gates. And then the next one, we have a carry look ahead adder. Okay, so that is a newer concept, and I am hoping that we can at least get to K1, K2, and K3 here, because a particular question of today's lab depends on this part, but just one of those questions. All right, so with that said, kind of the plan for today, we are going to go ahead and start with, you know what? I'm gonna, put the carry ripple adder to be after carry look ahead adder. So this way, I will be sure to cover all of these concepts before we kind of go back to talk about that. So let me see if I can change the order. There we go. So order is changed, except the arrow is not refreshed correctly. So now we got the arrow refreshed correctly. All right, excellent. So now we go back to the notes, and the first thing we need to deal with is k of I. Okay, because before k of I plus 1 defined using k of I, it requires arithmetic addition, which is kind of not what we want to do, because that requires us it makes it impossible to use transistors to implement whatever we need to do, because we do not have arithmetic addition yet. Okay, and you might say, but aren't we doing binary addition right now? Yeah, but that becomes a circular reasoning, because now it becomes a chicken and egg issue. So we're going to have to break that cycle by thinking about at least in base 2 addition, and see if the addition itself, between the two components to compute k of I plus 1, we'll find out whether that operator can be safely be replaced by a OR operator. So that's basically what this paragraph is about. Okay, so this paragraph here is about replacing this arithmetic addition to become a logical OR. All right. So with that said, I am going to use my tablet, because I think in this particular illustration, it is faster to use my tablet to draw out or to write the equations. So there we go. All right, so my face is covering a part of it. I can just move it very slightly. There we go. Okay, excellent. All right, so here's a new page, and I am going to re-quote k of I plus 1. So k of I plus 1 is defined to be, and there's good reason, because we have two sources of a carry to contribute to the carry of the next column. So we have the carry by adding xi, yi, and you can see the k is of I plus 1, which means this is the column to the left, and xi, yi belong to the column to the right. So we are talking about two adjacent columns here. And then this is a real plus. Okay, this is a real addition because there's another source of a carry of 1, which is when we add qi and ki. So right here, you can see how k of I plus 1 depends on k of I, because k of I plus 1 is what we want to figure out, and one of the components that is needed is k of I. All right, so that's going to be an important point to be discussed in just a little bit. But what we need to do now is to say, hey, can we replace this with a OR operator? Okay, the V symbol is also the mathematical symbol for disjunction. It's the proper notation, but in this class, most of the time I want to use just the plus symbol because it's way easier to type on the keyboard. All right, so we want to first compare the two operators. Okay, so we have, I wouldn't use x and y. Let's use u and v down here. And we're dealing with binary numbers. So I'm going to spell out the 4 possible combinations of all the values between u and v. So u and v, you can just look at those two as independent Boolean or base 2-digit bit, variables. So we're going to look at these two and go like, okay, if we just add, okay, let me maintain the order. So u plus v versus u or v. Oh, this is going to look kind of bad because this junction looks like a v. So I'm going to use bar here just to make it very clear that we are dealing with a disjunction operator. So you'll find out that, hey, 0 plus 0 is 0. 0 or 0 is also 0. 0 plus 1 is 1. 0 or 1 is also 1. 1 plus 0 is 1. 1 or 0 is also 1. So the only time that the two operators will behave differently is when u and v are both 1s. Because in that case, a normal arithmetic addition will give us a 2. On the other hand, if we use the logical OR operator, 1 or 1 is still a 1. So this, if we can avoid, okay, if we can say this row will never happen, based on what we are dealing with here, then we can say, hey, we don't really need arithmetic addition anymore. We can just replace the arithmetic addition with a logical OR. Okay, so that's kind of what we want to do, but we are not really sure whether we can do that or not. So here is a proof of why we can do that. Okay, so the premise is we want to make sure this doesn't happen. We have to make sure that it is impossible for this carry to contribute a 1 and at the same time this carry to also contribute a 1. We want to make sure that that does not happen. Okay, so the question is, intuitively, it seems to make sense. And if you try very hard to find a case to make both of those carry, both of those contributors to provide a 1, you would not be able to do that. But that is hardly a proof of anything. It is simply observations, right? That's just observations. So what we want to do is to rigorously prove this whole thing and say it is just not possible. Okay, so I'm going to use logic here. So I'm going to say if c of xi, yi is a 1, what does that imply? So you have to expand the carry function. So we have talked about this already. The carry function is the logical AND. So xi, yi. So this time it is Boolean. Okay, this is xi and yi. It's a 1. But what does that imply? How do you get a conjunction to give you a 1? All components of the conjunction need to be 1s, independently. So now we have xi being a 1 and yi being a 1, right? And then what does that imply? Well, that implies q of yi, which is defined to be r of xi, yi. That has to be a 0 because it is exclusive OR. R of xi, yi is xi exclusive OR with yi. Okay, we talked about the exclusive OR operator before. So, when xi and yi are both 1s, qi is guaranteed to be a 0. Okay, so what does that imply in return? Okay, so that implies that Qi, or I should say C of Qi Ki, which expands to Qi and Ki, becomes 0 because we know Qi in this case is false. It is a 0, and Ki, and 0 and whatever is always 0. It's always false. Oh, okay. So this is really kind of important because if we just focus on the important parts, okay, if we know that C of xi, yi is a 1, then we know that C of qi, ki has to be a 0. All right. Any questions about this kind of really short chain of logic here? I don't see any questions. Okay, we got. Do we need to check the other direction? Yes, Terrence, you are absolutely correct. We have to check the other direction too. Because all this does is to say, hey, if C of xi, yi is a 1, then C of qi, ki has to be a 0. But it doesn't really go the other way around. It doesn't mean that, hey, if the other one is a 1, then if C of qi, ki is a 1, then C of xi, yi also has to be a 0. It doesn't say that at all. Okay, it's because you can see how I'm using implications here. So the logic only goes in one direction. So now we have to go in the opposite direction. So now we say, what if we know that C of qi, ki is a 1? Okay, same kind of logic, right? Because now we know qi and ki is true. That implies qi by itself is true and ki by itself is true. And what does that imply? Well, we know how qi is defined, right? Qi is defined as the exclusive OR between xi, yi. Okay, so if qi is a 1, we got two possibilities here. Because the first possibility is we know that xi is 0 and yi is 1. That's one possibility. Or, okay, I'm going to use, I suppose I can use the mathematical OR this time because there's no confusion. So the other possibility is xi is a 1 and yi is a 0. What does that imply in return? That implies C of xi, yi, which is xi and yi, has to be a 0 because in either case we have at least one of the two being a 0 being false. So the conjunction between xi, yi is guaranteed to be false, which turns out to be the carry contributed by xi plus yi. So once again, the focus is the beginning, which is if we know that C of qi, ki, which is this component up here, is true, then we eventually can prove that C of xi, yi has to be a 0. So if this is a 1, this one has to be a 0. If this one is a 0, then this one has to be the other way around, sorry. If this one is a 1, then the other one has to be a 0, which basically completes the proof that they cannot both be 1s. Because if one is 1, the other one has to be a 0. Okay? So that means this row does not happen. If this row cannot happen in this specific case, that means the arithmetic addition can be replaced by a logical OR. So now we can safely say, hey, we don't need this, okay? Because this is leading to, how is it? Oh, okay. So we know that this can now go away because we can now replace it with just a logical OR. Do these equations apply to just binary or all bases? All right, so let's think about this. Well, okay, there are two aspects to this, okay? So the proof that we have here is specific to base 2 because we are using how we expand the carry function, in this case. But as it turns out, the replacement of the arithmetic plus with a logical OR also applies to all other bases. You cannot have xi. So in general, for any base, okay, you cannot have c of xi yi to be a 1 and also having c of qi ki also be a 1. That has to do with a few things. Okay, it has to do with, if you want to prove for that, it has to do with you can do it by induction. Basically you say k of I can only be a 0 or 1, and then q in this case can only go up to whatever the base is minus 2. And you will say, but why? Well, that's because when you add the largest digit of any base to itself, okay, each one is one less than the base itself, right? So that means the sum of the two largest digits in any base is going to be twice of the base minus 2. And that cannot be represented using one single digit, but it also guarantees that the single digit sum, which is what q of I is going to be 2 less than the base itself. So when you have a value that is only 2 less than the base itself, and then you add 1 to it, guess what? We still have one digit that can represent it, because it is, because then we have the largest digit that we can use to represent it. So I mean, yes, I know this is a really kind of loose proof right now, but the idea is this logic here, to replace the arithmetic addition by a disjunction, that works for any base, which is really cool. But the binary case is very easy to prove, so that's why I like this. Yeah, so I think Daniel is thinking ahead of time and basically going like, oh, okay, let me answer Jonathan's question first. Um, yes, so that only works. What Jonathan wrote can be confusing because the caret, which I think Jonathan is using here to mean a logical AND, is actually the bitwise exclusive OR operator in C, which makes it kind of confusing. So it's probably better to use ampersand instead of the caret, because caret is an actual operator. Thank you, Jonathan. Thank you. So yes, so that part only works in base 2. But using a different line of reasoning, we can still do exactly the same kind of reasoning here, except the stuff in between is going to be different. Okay, it will be based on an argument of the largest single digit sum can only be between x and y can only be 2 less than the base. So in other words, okay, I'll give you guys an example. 9 plus 9 is 8, from a single digit sum perspective. So when you think about 8, what is 8? 8 is 2 less than the base that we are dealing with, which is base 10. Okay, what about base 2? In base 2, the largest digit we have is 1, and 1 plus 1 is the quantity of 2, which is the base, and then when you subtract 2 from the base, which is 2, you have a 0. So the logic still works, right? And if you add 1, which is the k of I, to the single digit sum of between x and y, it can never bump it over to have another carry. That is just not possible. So once again, I said, this is a very loose proof, because we have this assumption that k of I cannot be more than 1. The whole thing depends on k of I cannot be more than 1. So we need a structure of this proof in order to say, yeah, we are pretty sure that k of I cannot be more than 1. And that part is, I think, the best way, the easiest way to do it, I haven't done it yet, is to use proof by induction, which is kind of beyond the scope of this class, but that's one of the topics in CISP 440. So there we go. Okay, anyhow, I like Daniel's comment that, hey, we cannot now we can implement it. We can actually implement it because we have removed the last circular logic, because now k of I plus 1 is really just xi, just to use C++ operators. Okay. So now everything boils down to Boolean operations. So for the first time, we now have every single piece being able to be implemented using logic gates, which is really cool. Okay, but there's a problem. The problem is k of I, this guy over here, depends of, oh, sorry, I should say k of I plus 1. Okay, so k of I plus 1 depends on k of I. So what that means is until you know what is k of 1, you cannot figure out what is k of 2. Until you know what is k of 2, you cannot figure out k of 3, and so on. There's a linear chain to this whole thing. So now would be a good time to introduce the concept of a propagational delay, because this logic here can be seen as, okay, so let me remind people again, you do not want to use this for the carry look ahead assignment in the future. Not today, okay? Next week we will have a homework assignment which is based on carry look ahead. So right now we're talking about carry ripple, okay? So do not repeat this circuit in that particular lab because it's not going to be useful. Okay, so let's go ahead and turn this into a logic gate thingy. Okay, so we got x, we got y as input pins. So input pins are always squares, and the AND is pretty easy to do. Just put an AND gate here. X feeds to one end, y feeds to the other end. So now the output becomes x and y. And we need another input pin for k, okay, because k is actually another component. But we don't need one for q because q can be computed based on x and y. Okay, so so just for laziness sake, okay, I'm going to use an exclusive OR gate, which looks like a OR gate except the inputs are has a kind of like a bar or curve to it. So this is exclusive OR, and we'll just say q is the exclusive OR between x and y. So we tap x here, feed it to one of the input of the exclusive OR, and then we tap y and feed it to the other input of the exclusive OR. So whatever is coming out of it is actually our q, even though in a circuit it doesn't need a name. But what we need to do here is to combine the q and the k using another conjunction. So now we have another AND gate here. And then finally we have an OR gate to combine the output of the two. So here's an OR gate, like so, and the output is k of I plus 1. So this is xi to be exact, this is yi to be exact, this is ki to be exact, and this is k of I. So that means when I is 0, then k of I plus 1, there we go. So when I is 0, this is how we compute k of 1, and when I is 1, then this is how we compute k of 2, and so on. But you can kind of see how this makes a chain, right? Because the k of 1, is needed to compute k of 2, and then we have another circuit looking exactly like this to take k of 2 as its input to produce our k of 3, and then we have another circuit, another clone, another instance of this circuit to take k of 3 over here and produce k of 4 over here. So it becomes a linear thing. And each gate has a propagational delay. In other words, from the time the input becomes steady to the time that the output is proper, has the right answer, there's a certain delay, and that delay is called a propagational delay because transistors do not work simultaneously. It needs time in order to respond to changes to the input. So there's a propagational delay here, there's a propagational delay here, but that is okay because these two gates can operate at the same time. This is something that we cannot usually do when we are programming because programming is very sequential. But when we are talking about logic gates in the circuit, they can perform operations at the same time. But this gate here, okay, this AND gate cannot start to operate Well, it operates all the time, but it will have to wait until the exclusive OR to have the right output. So that means in order for the changes that happens here to the time when this particular AND gate to have the right answer, there will be two. Okay, so I'm going to put 2t over here because we need the propagational delay of the exclusive OR gate and also the propagational delay of the AND gate. Now, because the output of this AND gate needs to be right before we can even work out the output of this OR gate here, so that means between the time that the input pin changes all the way to the output of this OR gate being correct. Now, the OR gate always, every single gate always has an output. The question is it correct? Okay, does it reflect the correct result based on the input? So this is going to be 3t. Now I am making an assumption. A t is the propagational delay of one single gate. In other words, from the time that the input of a gate has settled to the time that the output of the gate is correct based on its input, there's a certain delay, associated with that. Because gates do not operate, in no time. It does need some time in order for the output to be correct based on the input. Is that okay, Daniel? Are we good with what t is representing? What is propagational delay? Okay, very good. So propagational delay is not a term that I invent. Sometimes I do that, but it is an actual term that you can find out in. And you call some and gates and some OR gate. Well, we have this as an AND gate to reflect what we do here. We have this as an exclusive OR gate to compute the Q of I. This is another AND gate for this particular AND operation, and this is an OR gate to take care of the overall OR operation. So yes, we have all kinds of gates here, and I'm making the assumption that they all have a propagational delay of t, which in reality may not be realistic, but to make it a little bit simple, I just make it the same. Okay, all right, cool, no problem. So, but that means in order to get to, let's say you're dealing with a 32-bit adder. Okay, so in order to get to K32, we need 32 times 3t for that very last or the most significant carry bit to be correct. Okay, because the more bits you want to add, then you have to replicate this circuit more times and then chain them together. And that is the essence of a carry ripple adder, because if you look at it from the time perspective, you can kind of see the moment the x and the y changes is the kind of when you drop a stone on the stationary or calm surface of a lake, and then and then each level, each circuit like this, basically they're chained along, in a certain direction. That becomes the ripple effect, because you will see, oh, okay, now that we have K1, we can figure out K2, and then once we have K2, we can figure out K3, and so on. It becomes sequential, which is really kind of bothersome, because now it means when you have a 64-bit adder, it's going to take twice as much time as a 32-bit adder, which is going like, that kind of sucks, especially if there's a faster way to do it. Okay, so exercise 5.1 is really just to implement a 3-bit by 3-bit binary adder using AND or NOT, and I'll give you exclusive OR 2 gates in Logisim. It is not something you have to turn in, but I thought it would be nice if you can at least think about it. And what we'll do is we are skipping to section 6, because this is really just a ungraded assignment, which means you can read about it and try to do it by yourself. But you don't have to turn it in, so it's no biggie if you cannot finish it. We do have a long weekend coming up. You guys do not have as long of a weekend as my Monday-Wednesday class, because Monday is what is it? Labor Day, right? So but still, you have like 4 days, in between. So that means, well, if you want to kind of sharpen your skills and your knowledge in this class, this exercise may be worth your while to do it. Okay. So what we're going to do now is we're moving on to section 6. Okay. So section 6 is borrowing a phrase that is commonly used in infomercials. And every time we see this, okay, but wait, there's more. We kind of know that, yeah, we are probably only halfway through the show, especially in infomercials. And that's exactly where we are now. We're just halfway through the whole thing. So the first thing we do is we take the original equation of k of I plus 1 depending on c of blah blah blah, and in this case we are already converting everything to Boolean. Okay, so these are all Boolean expressions. They are not regular arithmetic expressions, because we already showed earlier using the tablet that we can safely replace the arithmetic addition with a logical logical OR, and that's exactly what we have done here. This is a logical OR. It is not arithmetic addition. Okay, so I'm only borrowing the operator, to mean disjunction in this case. All right, so. And at this point, from the first line to the second line is just an expansion, because we know how C is defined for base 2. So all of these are base 2, because otherwise we cannot reduce these things to logical expressions anyway. So from line 1 to line 2 should be fairly obvious. From line 2 to line 3 should be fairly obvious too, because that's exactly how Q is defined. From line 3 to line 4, this is how we can do one way to do exclusive OR. And because I want this whole thing to be to basically just use usual Boolean algebra, so I basically use x and not y, or not x and y instead of the exclusive OR. They mean exactly the same thing. We talked about this in the previous class already. And then from the 4th line to the 5th line, I am using Boolean algebra in this case. And relax, you're not expected to understand Boolean algebra in this class, but eventually you need to understand Boolean algebra in CISP310. So look at this as a preview for the other class, or as a review if you have already taken CISP310. So this is distribution, which works kind of the same way as arithmetics. Okay, you can distribute an addition over, you can distribute a multiplication over addition, and in this case, you're distributing a conjunction over a disjunction here. And for all of these rules, in Boolean algebra, you can actually prove these things using just a truth table. So if you say, I'm not really so sure about this, equality between these two expressions in Boolean algebra, you can always just say, okay, I'm going to prove it by myself, because I can always use a truth table to do it. That's not a luxury that you have in regular algebra, because you cannot just enumerate all possible cases in regular algebra when the domain and the codomain are real values. But in Boolean algebra, it's just 0 and 1, so it's pretty easy to spell out all possible cases to prove two expressions are indeed equivalent to each other. Alright, so moving on. So from here to here, I'm just introducing the identity of conjunction, which is true. In other words, blah blah is always the same as blah blah and true, because and true doesn't do a single thing to affect the value of the expression. And this part here is a little bit confusing, because it doesn't work in normal arithmetics, but it does work in Boolean algebra. In other words, if you have something that is true to begin with, true or whatever is always true, because you only need one side of true to be true for the whole thing to be true. Okay, I see. Who's this guy? SpongeBob's best friend. My memory is really bad. I can remember the context and stuff like that. Patrick, that's it. That's right. There are theories that Patrick actually has an extremely high IQ, and he's only pretending not to be very smart. Yep. Yes, this class is, basically all the classes that I teach are very heavy in math, okay? But remember, this part in the derivation, you don't need to remember or even understand the derivation. But eventually, at some point, okay, probably in CISP 440, this may become important. Exactly. So because once you have a true value, true or whatever is always true. You cannot um, turn something from true to false by ORing it with something. That's just based on the truth table of OR. So for anyone who's curious about from here to here, how true is the same as true or something, you can just use a truth table to put it to prove it. Okay, that really is doable, and I advise you guys to do it if you are not convinced. It's called domination law in Boolean algebra. Interesting. Okay, I never really care much about names of those laws and whatnot, but thank you, Richard, for mentioning that. So people who want to look it up now has a name to look up. I guess that's one of the advantages of having a name. So anyway, I'm moving on. So from here to here, it is just distribution again, because the 1 goes on one side and then the k of I goes to the other side. We're distributing this over xi, yi. And then from here to here, I'm duplicating an item. So we see that in the original one we only have one conjunctive term of xi, yi, ki, and here we have two. Now obviously this is not going to work in normal algebra, but in Boolean algebra it works, because if x is a Boolean variable, x or x is always the same thing as x itself. Now it also works for x and x. Okay, so but in both cases, you can always make things look more complicated, but it retains the original value. And then from here to here, it is just associative law, which basically means, no matter if you have a whole bunch of ORs, it doesn't really matter, about the order of which one is done first. Okay, that's associative law. And if anyone is not convinced about the associative law in Boolean algebra, once again, you can prove it using a truth table. Pretty easy. Okay, so from here to here, it is factoring, which is the reverse of distribution. So over here we see that both of these terms have xi, ki in it, right? So this one has xi, ki, this one also has xi, ki. So we use factoring to extract xi, ki as the common term, and then the differences between yi and not yi are extracted, so that we are now it becomes a different form of the same thing. It's the reverse of distribution, and we do about the same thing on the other side. This is also a simplification that only works in Boolean algebra, because y or not yi is always true, because one of them has to be true. If yi is true, then the whole thing is true. If yi is false, then not yi is going to be true, which means the whole thing is going to be true. So regardless of whether yi is true or false, the entire expression has to be true. Same thing over here. So now we have, we combine this into just true, we combine that to just true, and true is simplified out from a conjunction, because true is known as the identity of conjunction, so we can safely leave it out without changing the value of the expression. And then from here to here, once again, we have factoring again, because we know that ki is a common term, so we extract ki to be on its own, and then we look at the different terms and go like, okay, we'll group those into its own disjunctive term, and then have the disjunction to be ended with the common term. So once you understand Boolean algebra, this is fairly mechanical. But what is the bottom line? The bottom line is, Tech, you haven't solved the problem, because we started off with k of I plus 1 depending on k of I. We end up with something that looks like this, which means it is still dependent on k of I. So you go like, but Tech, what is the whole point of doing this? I think that's what Patrick would have asked, right? Patrick would have asked, go like, what is this all about? My head just blew up. Well, it's all for a good reason, which we will talk about in just a moment. Because we're going to take row at this point. Your favorite activity of the day. Tag is taking row. All right, so here we have the row taking activity, and well, this time I'm going to do it in a slightly different way. So I'll release it first, and then I'll show you the answer. How about that? So this way, you guys can. Oh, come on. You guys can get to the activity first, and then I'll show you the answer. So now you guys are all, I'm hoping you guys are all having your your cursor, to be in the question prompt and say, okay, but what's the answer? What is the answer? The answer is Zeus. Okay, I'm not sure whether that's the proper pronunciation, and I'm trying to paste it into the text channel. There we go. So just copy and paste it, and you guys might be asking, but what is this word? What does it mean? That is the guy, or what people believe is the person who invented the carry look ahead mechanism. So it has significance in this class. All right, so I'm gonna take this window away so that you guys can do it. I don't think a desktop computer is going to do autocorrect. Fastest clicker in the West. See, my son would have used an auto clicker for that, an auto key program to do all that. No one actually can confirm, who is first. I don't think you guys get a feedback of, oh, you're the first. I don't think I can see that either. I can only see, people have answered, but I don't think I can see, when, with resolution down to the second or sub-second of that. And I see a few people are not responding. Okay, well, that counts as an absent, unfortunately. All right. Okay, so I think we are good. Nobody works for Canvas because Canvas is the name of the product. It's just like, no one works for F-150 because F-150 is a truck made by Ford. The truck cannot hire people. The company who makes Ford, the company that makes F-150 can hire people. The company that makes Canvas is Instructure. So think about instruction. Replace ION with URE. Instructure is the name of the company. All right. Nope. Google has Google Classroom, which is a competing product compared to Canvas. I personally like Moodle, which is another platform for teaching classes, and Moodle is 100% open source. In other words, anyone can just download the code and make your own site, for teaching classes. Used it for years, and then when they started to convert to Canvas, they took Moodle away from my hands, unfortunately. Yes, Moodle, well, it was never really abandoned by Los Rios as a district because as a district they never used it. I was the only person with maybe about, 8 or 9 other professors, using Moodle. And when we converted to Canvas, as per the contract with the OEI, Online Education Initiative, which used to be a grant program. So as per the licensing of using Canvas for free, for this district, we had to remove every single other LMS from our systems. And guess what the reason was? Okay, I know I'm kind of digressing a little bit here. The reason I actually asked, okay, I said, but Moodle is free. I'm not charging the district a penny to run it, so that becomes my own, LMS. What is the problem? And eventually they explain and they say, we want to funnel every single student interaction with the LMS through Canvas so they can collect data on you. That was the reason why they had to get rid of every single other alternative of a learning management system. It was all about collecting data from you. And the organization behind the scene collecting all the data, guess what? Its name is, the name escaped me right now. Oh, okay, Lumina Foundation. Okay, you guys will like this, especially those of you who self-claim to be a conspiracy theorist. So it's called the Lumina Foundation. There we go. So Lumina Foundation, was basically collecting all your data, interacting with Canvas in the back end. And the interesting thing about Lumina Foundation was it was a spin-off from a student loan organization. So when the student loan organization went from non-profit to for-profit, by law, they have to spin off a non-profit sub-organization to continue, quote unquote, their non-profit activity, and that turned out to be the Lumina Foundation. And the Lumina Foundation is the one behind the scene collecting your data. So there you go. There you have it. And you can quote me because none of this is an accusation. These are all facts. So getting back to where we are. So now we are getting to some really important stuff here. So I'm going to define g of I to be the conjunction between xi and yi, and I'm going to define p of I to be the disjunction of xi, yi. So in other words, g of I and p of I are pretty easy terms. Okay, it's just a definition so that this particular expression becomes this expression here, because xi and yi is really just g of I, xi or yi is really just p of I. So you guys would say, but Tack, that is one extra useless step because I have not solved the original problem of k of I plus 1 depending on k, which makes the whole chaining thing, happens. So, okay, I'm just going to check out the oh, no. Educational institutions is if they plan and execute the plan correctly, it is a student loan generator. Okay, yep. So you guys made the right decision going to a community college, to begin with, because you're less likely to rack up a very high student loan, at least not until you transfer out of a community college. Yeah, what can I say? All right, so getting back to this. Right. So the first thing we do, we look at this equation and we plug in specific values for i. So when I equals to 0, what do we get? We get k of 1 because 0 plus 1 is 1, and I is 0, so we have g of 0 instead of g of I, and then we have p of 0, k of 0. So when you look at this, you go like, yeah, so, okay, by itself, not really too impressive. By itself, it's not, it doesn't really come out as, something that's really, kind of significant. So now what we do is we plug in, what if I equals to 1? So if I equals to 1, then I plus 1 is 2, I is 1, I is 1, I is 1. So now we have k of 2 being the same as g of 1 or p of 1 and k of 1. You go like, yeah, so, well, once again, by itself, not a big deal. But we can use substitution now, right? Because we know what is k of 1. So instead of just continuing to use k of 1, we say, hey, hold on a second here. We know what is k of 1. K of 1 is g of 0 or p of 0 and k of 0. Alright, so what is the big deal? You just make something that looks simple looking more complicated. Well, let me make it, we'll perform one more step, which is distribution. So once we use distribution, then k of 2 is now expressed as, oh darn it, I forgot about the subscript here. I'll fix it. So k of 2 is now defined as g of 1 or p of 1 and g of 0, or p of 1, p of 0, and k of 0. Oh, where's k of 1 down here? It's gone. So k of 2 using this method no longer depends on k of 1. It only depends on the p and the g terms. The p and the g terms are easy, right? As soon as we have the xy, we can compute g, we can compute p. So those can all be computed at the same time as soon as we get the values of xy, which is a whole bunch of bits, the p and the g terms can be computed within one single propagational delay. So they are not really that big of a problem because there's no chaining involved when we are computing the p and the g terms. But the most significant part here is it also only relies on k of 0. It doesn't depend on k of 1 anymore. So that whole chaining effect thing seems to be gone, right? Seems to be gone. Alright, so I'm going to read a little bit about the text channel here. It's not moving indexes, it's basically substitution. If you guys are referring to what we are still talking about here. Alright, so what about k of 3 then? Okay, so if we use I equals to 2 and substitute 2 plus 1 here, then we are computing k of 3, which is here. And then g of I is g of 2. And then p of I, k of I is p of 2 and k of 2. So we start with this, which looks like, yeah, so I can see the substitution. What is the big deal? Well, by itself, not that much of a big deal. But now that we can express k of 2 without using k of 1, we can now substitute k of 2 with this expression, which is what we got here, right? Oh, okay, you guys are still using shortcut key and stuff like that. Okay, so we can copy and paste this over here because we know how k2 is computed. So we basically substitute the expression that turns out to be just k2 in place of k2 when we want to compute k of 3. And then we apply distribution again. So this time we end up with, a longer expression, which is g of 2 or p of 2 and g of 1, or p of 2 and p of 1 and g of 0, or p of 2 and p of 1 and p of 0 and k0. So yes, it is a longer expression, but it doesn't take longer to evaluate when it is implemented in hardware. Because when you implement this in hardware, this gate, this AND gate computing the conjunction here, and this AND gate computing this conjunction, and this gate computing this conjunction, they all work at the same time. Okay, so given that we have the p and the g terms already, one propagational delay will compute conjunction, conjunction, conjunction all at the same time. And once we have the results from all of the conjunctions, we just need one single disjunction to combine all 4 different values, and now we have the output. And this is without needing the chain, because k of 3 no longer depends on k of 2, and that's why we basically no longer have a chain. So the important part of this discussion is the derivation in between is really here to show you how we got from here to here. But it is the last expression that is important. The last expression is what makes carry look ahead works. Okay, so I have to emphasize this because in previous years, I have people implementing the circuit based on the first or the second line. It's like, okay, so think about this. Okay, if I only care about the first or the second line, why would I even bother to have the third line, which is the end result of the derivation? So it is the finished product, the third line, that matters. Okay, because that is the one that removes the the multiple level of gates in order to compute all of the k values. So now that we have this, okay, I'm looking at the time. Yeah, we got plenty of time. I'm actually a little bit ahead of schedule. Very good. So, so you can kind of imagine k of 4 looks kind of more complicated, but you can probably guess that k of 4, after we expand everything, will just end up as a single disjunction of a whole bunch of terms, and each term is really just a conjunction of the p, g, and the k terms. I mean, just from looking at this thing here, that's kind of the sense you might get, right? In order to get a sense of what k of 4 may look like. All right, so I'm looking in the text channel. Oh, okay. Not really sure what you guys are trying to do. Oh, superscript and subscript. Yeah, well, that's also why I prefer to use either FreePlane or to use what was the other one? Jotlin. 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 Was it Jotlin? Yeah, Jotlin. For note taking, because it's easy to type it in. Okay, let me illustrate. I know this probably still won't convince you guys to use it, but Okay, so let's just say I want to turn this into general k subscript I plus 1. So what I need to do here is to put a LaTeX to indicate what follows is in LaTeX format, and use a $sign to begin an equation, and then after that underscore, and open curly brace. Curly braces are basically used to group a bunch of stuff, and underscore means whatever is right after the underscore is supposed to be subscript, and another $sign to end the equation, and voila, we have k subscript I plus 1. You can actually enter pretty complicated equations here. So yeah, I know it's difficult for you guys to learn all of this, because while you're learning, you kind of have to spend some time to actually look at it. But since I use those notations here, you can just right click here, click on show math as, and then click on tag command, and that will show you basically how the whole thing was entered on my side. So instead of using begin align asterisk, you cannot, I don't think you can use that in FreePlane, but everything else, okay, the actual content between the begin and the end, that you can use. So that it's one way for you guys to learn how to put in mathematical equations using the LaTeX format, which may come in handy at some point in time. Yeah, Overleaf is basically the web-based interface for authoring LaTeX documents, so that you don't have to install LaTeX on your own computer, which by itself is kind of a chore. It's not super duper difficult. It's just a chore. So if you don't want to keep your own installation of LaTeX, what Terence said about Overleaf is correct. It is a pretty useful tool, web-based, and it's pretty visual too. So if you don't have to go through a bunch of command line commands just to find out, oh, I got that notation wrong, which happens to me sometimes. Okay, cool. So let me fix this first, and then we'll get to this nasty little thing down here. But at this point, okay, we know enough to finish today's lab, okay, because today's lab is about multi-bit gates. And the last question relates to what we have just talked about. So let me switch to the, oh, where is it? I'm looking for my command line prompt, and apparently it is, I must have moved it somewhere entirely out of the screen. Alright, so give me a moment to find it. There we go. Alright, so let me go back to the notes. because this is how I type my notes. At least in the past, this is how I do it. I might want to change it at some point in time, but it's not in a hurry. Teachers, modules, and the module name is 0283, and the module content is where the actual content is, because I have a little template, so this is actually just a part of the template. And I believe the one that has a problem is G1. Okay, so we're looking for G1 without the underscore. And there we have it. So put in the underscore, and then I have a script to do all the necessary steps to republish something. So I just have to do that. This is the tool to turn LaTeX into HTML format, which is really kind of handy. I used to publish everything in PDF, and then I got into some accessibility issues with PDFs. So now I don't have to worry about that anymore because I only publish in HTML. Oh, wrong one. There we go. And we want to double check, make sure that the one part that I want to change is indeed changed. Yep. So there we go. We have the G subscript 1 here. All right. So now let me take a look at the time. Yeah, we got plenty of time. So now we look at this nasty little thing and go like, what is that? Well, that turns out to be the generator. Okay, I'll call it the generator to come up with k of n plus 1. So substitute n with any natural number and it will work. Okay? So now the next thing is, what are these notations? We have never seen these notations before. A big V and a big inverted V with some indexing and stuff like that. That's kind of the same thing as a sigma notation. In other words, this big V is the summation, not summation, I should say disjunction of all of these terms here. And every single term that we are ORing with each other depend on the variable I, which increments from 0 to n. So this is basically specifying kind of like a loop where each iteration is represented by a particular term, and that term usually depends on the index I. And sometimes we would have a nested term in here that depends on I also, but it has its own kind of internal loop where it starts at a certain point, ends at a certain point. And just from the shape of it, you can see this is an OR operation and this is an AND operation. So that's kind of the deal of this particular notation. Questions? What does n mean in that equation? So n is a natural number. So whatever k you want to figure out, you want to make n 1 less than that particular index. So for instance, if I'm making a 32-bit adder and I want to figure out what is k32, I just have to make n equal to 31, and then this will give me something that looks like this, except it's going to be much longer and much more complicated. So this is sort of the quote-unquote closed form to figure out what is k n plus 1 using the carry look-ahead mechanism. Yep, there you go. All right, so let me try to explain how to make this work. Okay, so I'm going to look at this from a coding perspective because we have all taken C and C++, which is CISP310, and I'm going to use that assumption to explain this one. So let me open up mousepad, and then I change the size of mousepad. So because I want to keep an eye on the expression or the formula down here, and I want to be able to show the indexing. There we go. So that's probably the best way to do it. And I want to make sure that you can see the top of mousepad. Yep. Okay. In fact, I can get a little bit more space up here. All right. Okay. So what does this mean, right? I'm just thinking about what programming language I want to use, because certain programming languages are easier to use to explain this, and other languages are a little bit harder. Since we talked about C and C++, let's just stick with that. Okay, so I'm going to use just regular C and C++ to try to express this. Okay, there we go. Okay, I have to be careful with the mouse movement here. Alright, so let's move this up just a little bit so I can see that. Okay, there we go. Alright, so I am going to, we'll do it in C++. Okay, what is the concatenation operator in C++? String concatenation. Is it just the plus operator? Or does it not even have a single operator for string concatenation? Okay, just plus. Thank you. Alright, so I'm gonna say, now the syntax may not be 100% right because I've been programming a lot in JavaScript, and JavaScript in many ways is really just superior compared to C++ for especially text processing stuff. Okay, so I'm just gonna pretend that I still remember how to do this in C++ here. Yeah, I'm not couting, I'm just gonna do the operation in here. There we go. Alright, so all this is going to do is to give us something that is equivalent to what the expression here is saying. So it may so things may be out of order just a little bit, but I just want to illustrate the concept. So now we have a for loop. So we say for int I equals to 0, I is less than or equal to n, because when I equals to n, that is our last iteration. So I need I to be less than or equal to n, not just less than, and then plus plus I as the post operation. And then in here, I'm going to have the first term. All right, so in here we have I'm just trying to figure out what to do with this here. Okay, we'll do the inner loop first. Okay, so the inner loop is using j as an index. The starting point of j is I plus 1, and then as long as j is less than or equal to n plus plus j. So now we have the nested loop. So I'm going to handle this part here first, which is just p of j. So we'll go ahead and say, probably don't want to use result at this point, so I'm just going to say term. So we're going to have term concatenated with itself, and let's see, what am I going to do here? Not sure whether we can do it this way. I'm just going to guess that we can. Okay, so p of j. How do you convert a numerical value into its string value in C++? To string? Okay. So I am guessing in some other languages you have to use int to create an object first, because otherwise there's no toString as a member. So I'm going to use this is going to be j. Like so. Oh, okay. ToString is already giving me a string, so I don't need to make it a string. There we go. STOI, ITOS. Because we're converting from an integer value to a string. But the idea is, this is really just j, concatenated with a p. Okay, that's all it is. And all of those items are are ended together, so there's nothing in between those particular items. And then the outside, I need a g of I too. So so that means term is going to be g of I, which is string g plus int I dot toString. I keep forgetting the semicolon at the end of a statement because in JavaScript it is not needed. All right. So what this code so far has done is to compute each inner term like this. Okay, and then the overall we need to OR the with the all of these subterms here. So after we get each term, then we have result plus equal to. We have to remember the plus in between. So we can say this plus just the string of plus itself, which is not always needed because the last one does not need it. So we can tell whether it's the last term or not. So we can kind of use a ternary operator for that. We can say if I is n already, then we'll have an empty string. Otherwise, we have a plus, because we need the plus to join with the next term. All right, so term plus equal to. I'm not sure what that means. Oh, right here. Okay, thank you. No, it's not plus equal to because I want the g to be first, so I want a plus term down here. But thank you for the reminder because I needed that. Okay, so at this point, okay, for this inner loop here, we are now done with the first portion here. And because the next portion also need the plus, so it turns out I really don't need to terminate this with this, but that's okay. Since I have it already, might as well just kind of keep it. So now we say result plus equal to string plus, like that. That would take care of this plus here, this OR operator. So now we have another inner loop, but this is not a nested loop. This is just a single level loop. So now we can reuse int I as my index, and it starts with 0 again here. And then we say I is less than or equal to n plus I. And in this loop here, I probably want to have an extra variable at this point. So I'm going to have a string term here. And that term is going to be just all the p of i's together. So term plus equal to string p, and we want to concatenate with whatever the value of I is. So we have int I dot toString. Assuming this is how you convert an integer value into the string equivalence of the integer value, which I'm not 100% sure. So now that we have this kind of nested AND expression done, we just have to AND it with k0 and then attach it to the other one. So we now have result plus equal to. This plus sign is already taken care of here. So we just have to specify k0, string k0. Come on, cannot type. And then concatenate again with whatever the result of the loop is giving me, which is term. And that's it. Okay. So I'm pretty sure this is not going to compile because I am not really that much of a C++ programming person. I program mostly in just plain C, not C++. So a lot of the classes, the use of classes in C++, I'm actually fairly not familiar with. Okay, now the same code is very easy to do in JavaScript. JavaScript makes this look like child's play. But since JavaScript is not a prerequisite of this class, I cannot make assumptions about that and use JavaScript. All right, so is this okay? Do you guys understand how this is implemented by this code over here? Clear as mud. Well, after you let mud sit for a while, it does separate into just the border and whatever sinks to the bottom. So in that case, clear as mud is clear. Do we ever have to do this in real life? Well, let's imagine that you are working for Intel or AMD, right? Okay, so some of you are computer engineers, some of you are computer science people, some of you are electrical engineering people, because I think all three need to take this class, okay? Because in Davis, electrical engineers actually have to take assembly language programming. So if you work for Intel, if you work for AMD, or even if you work for Google, because Google makes its own chips now, right? Because the new Pixel 6 phone is going to come with its own neural net specific chip, okay, to do all the neural net computation. And do you think addition is important in the calculation that is needed for a neural net application? Of course it is, right? So let's just say that one of these, employers say, hey, I need you to come up with a chip. Okay, we want to design a chip to do blah 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 blah, and addition is one of the things that you need to do. So assuming that it doesn't have a library currently to just say, oh, just plug in the width of your adder and we'll just spew out the gate logic. Guess what? This is going to be helpful, right? This is going to help you create, the circuitry that is needed in order to perform well, this one only helps you compute, k of n plus 1. That's all it can do. However, you can kind of imagine how this can be a part of a larger specification of a chip in order to do, just, 64-bit addition or something like that. So the answer is it depends on your job, okay? Now, not everything you learn in college, including this class, and some people will say especially this class, is going to be directly applicable in real world. It just is not, okay? So what I really want to teach, in addition to the content of this class, is how to think. That is important, okay? Let me look at the time. Yeah, we got 30 seconds. I can waste those. I can burn those 30 seconds for this. Because of rampant cheating and other things, employers really do not look at your GPA, the same way as they did 20 years ago. So if you get your bachelor's degree, that's really just enough to open a door. Okay, that's all it does, is to say yes, you have met the minimum requirement to get a job. Okay, from that point on, they will probably look at other things, and ultimately, these employers, especially Google, Facebook, Pixar, all of these really kind of high-tech companies, they have their own quote-unquote entrance exam for people who want to get a job at these companies, and those exams are hard. Okay, so and they're in person, impossible to cheat, and so on and so forth. Okay, so that means people who do the minimum to get through college, to get a bachelor's degree, all they're going to do is to be able to open the door and then only to have the door slam on their face. So what do I want to do? I want to equip you guys with the ability to learn and think independently. So by the time you get the door open, it won't slam on your face. In fact, I would hope that you guys would look at those exams and go like, yeah, so I know exactly how to answer this question. I don't need to, take a class or read a book, because I can think, okay? Because I can solve problems. That is the important part. So from time to time, okay, I will even say, yeah, this stuff is not going to be relevant at work directly. But it doesn't mean it is not important in the sense that it might help train you how to think. So there you go. Okay, so I'm not saying this to specifically criticize anyone. I'm just telling you what is the truth, because I have talked to employers, and that's what they told me. It's like, yeah, we don't really look at GPA too closely anymore. Okay, to rank employees, we'll give them our test, and see how they perform in our test. And they have books. You can look up Amazon, and they have books to help you quote unquote prepare for these exams. I'm not sure how useful they are. So anyway, we do have a lab today. So getting back to the relevant stuff for this class. So even though it is my intention to try to, I'm just trying to find the tab where the lab is. Okay, I might have lost it. That's okay. I can always just kind of get back to this one. And today's lab is multi-bit stuff here. And the discussion of the k bits, using carry lookahead is particularly important in this particular lab. So in this lab, you are allowed multiple attempts, and I am not going to show you the correct answers, or which answer you answer wrong, until after the thing is done. So the access code is multi, so I'll put multi down here, and it is already set up for the correct due date and time. So I'm gonna save and publish it. There you go. So you guys can get started. I'm going to walk away for about 10 minutes or so. Get something to eat, get something to drink, and then I'll be back to answer questions if anyone has any questions. So I will stop streaming to YouTube.